Wi-Fi 7 is now. Welcome to our today's webinar. Today, we are excited to share our knowledge about global regulatory compliance tests of Wi-Fi devices. We believe the information we provide you today will support your regulatory test task of your upcoming Wi-Fi products. My name is Feng Xie, Market Segment Manager for Wireless Communication. My focus is on all the regulatory test requirements of global market access. Beside me is my colleague, Jörg Kopp. Jörg has over 20 years professional experience of Wi-Fi technology. So in this session, we will start with some market and technology trend of Wi-Fi 7, followed by an overview of latest regulatory test requirements for Wi-Fi product in global markets. After this, we will discuss the test challenge and some test cases examples. At the end of the webinar, we will highlight some of our important test solutions which support you Wi-Fi device testing task. Jörg, as an experienced Wi-Fi expert, could you give us an overview about the current Wi-Fi 7 technology and the market status?
Yes, of course, Feng. It's a pleasure for me to give you a short introduction in the topic with a special focus, of course, on the regulatory testing so that we have all the same picture what Wi-Fi 6, Wi-Fi 6E and Wi-Fi 7 is about. As always, I would like to start with a market view, where we are standing today and what we can expect for the next couple of years. If you are looking on the number, simply the number of Wi-Fi devices which are actually in use in this year, we are already at around 19.5 billion Wi-Fi devices. It is forecasted that around 4 billion devices will be shipped this year. And what is more important, that a large part of these devices are already Wi-Fi 6 devices, so the latest standard, which were defined essentially for bringing more efficiency to Wi-Fi. And also a couple of these devices, around 80% is expected, is already supporting Wi-Fi 6E, the 6 GHz band, which is also the topic of this webinar today. If you're looking on Wi-Fi 7, and this is the topic of today mainly, we are expecting that Wi-Fi 7 will really enter the market in the next year. We have already a couple of announcements of chipsets, also announcement of access points and also mobile devices, but the real products we are expecting in the end of the year, beginning of next year. If we look on the standard itself, we are actually still in the draft standard. But even so, we have a draft on the table. Most of at least the physical layer stuff is already well defined, so that it makes sense to talk about this. So what is Wi-Fi 7 all about? Wi-Fi 7 is now looking again, not so much on efficiency. The main focus is throughput, and they call it about extreme high throughput. And what extreme high throughput means, we will see in a second. Main applications for this are, of course, streaming, working in our days, schooling, what we have learned over the last 2 or 3 years becomes more important, sharing information, but also using Wi-Fi in an IoT or industrial environment, looking on low latency applications is a topic, and not to forget, of course, gaming. All these nice glasses that we actually see on the market are usually used in Wi-Fi technologies for connecting with the related devices. So it's extreme high throughput at home, offices and factory. If you're looking on the physical layer, what you can do to improve the throughput to come to extreme high throughput. There's a simple formula which is essentially applicable for all wireless technology, how you can improve the throughput on the physical layer. One topic is the number of modulated bits, which is more or less a modulation scheme, so how many bits you can bring in one symbol. And here we will move in Wi-Fi 7 now to 4096 QAM, which is really a challenge from the RF point of view, also for the test and measurement equipment, because you need a very good RF design on all the sides. For example, you need an EVM for the devices of minus 38 dBm, which means for test equipment you are already in the range of minus 40, minus 50 dBm. Then the other thing is you have more resources, which is essentially the number of data carriers or the spectrum that you can use. And here Wi-Fi 7 is going now to 320 megahertz, which is a lot. And also have in mind, if you look later on the spectrum, 320 megahertz continuous bandwidth is so far in 2.4 or even in 5 gigahertz not available. And then what you can also do is add spatial streams, but this has a kind of limitations because your device has some physical limitations, how many antennas you can really integrate. So they defined this in Wi-Fi 7 now with 16 by 16. What we really expect on the market, for example, in these glasses, and therefore you see these pictures here on the left-hand side, that you can have, for example, devices which are supporting 4x4 MIMO. This will be the mainstream. To just shortly summarize this, what we have now with Wi-Fi 7 compared to Wi-Fi 5 and Wi-Fi 6 and Wi-Fi 6E, we are supporting all the bands, 2.4, 5 and 6 gigahertz. We are going now for 320 megahertz bandwidth. OFDM and OFDMA as introduced in Wi-Fi 6. The same guard intervals. Then we are extending the possibility of spatial streams to 16 by 16. And we have a new modulation scheme of 4096 QAM. Now I would shortly highlight the main topics which are relevant for regulatory testing. One thing is, of course, the 6 GHz band, which was introduced already with Wi-Fi 6. So far, we had the 2.4 GHz band, which were mainly used, but as very limited resources, of course. You see, you can just use 20 MHz channel, essentially. Then we had the 5 GHz band here, which brings you now also the possibility, for example, to use 160 MHz channels. Even they are just 3, so also very limited. Also having in mind, and this will be a topic later, that we have here radar communication in this area where you have this DFS schemes. Feng will talk later about this in detail. And now the regulators around the world were allowing in different schemes to use also the so-called 6 GHz band. And this is essentially, especially if you look for FCC, 1.2 gigahertz, which is available now. In Europe, it's not so much, it's around 480 megahertz, so quite limited, just the lower part. But this is what is essentially now available. And with this, looking on Wi-Fi 7, it is also possible to have now here 320 megahertz channel. Essentially 6 overlapping 320 megahertz channels, so also a kind of limited, but you are able to use 320 megahertz channels and so use the full power of Wi-Fi 7 only in a 6 gigahertz band. Not to forget, Wi-Fi 7 has of course some other features which are also relevant for the 5 gigahertz band as well, for example. If you are looking now and just briefly on the standardization and compare a little bit what FCC and what Europe is doing regarding the 6 gigahertz, and this is relevant for Wi-Fi 6E and Wi-Fi 7 as well, then we see here more or less two pictures. I mentioned already that the FCC is looking on the full spectrum of 1.2 gigahertz. Then they define one mode which is called standard power, which is a standard power access point with up to 36 dBm power. But the special thing is here that we use a kind of dynamic spectrum management or automatic frequencies selection or coordination. That means that before the standard power access point goes on air, they have to connect to a database, which is supported by the regulators, and ask whether they can use on this location a certain frequency and get back which channels they can use, which power, and so on and so forth. Just a short description for this FCC, so very special. And then we have low power indoor. This is allowed only indoor, which also means there needs to be a cable connection to the power cord and also a fixed antenna and so on and so forth. It's, for example, also not allowed in automotive and vehicles, in airplanes and so on. You have to look on the details on this. So that's really about indoor. And this is with a limited EARP for the access point of 30 dBm. In Europe, it's a little bit different. First of all, I mentioned already, they're just this 480 megahertz. They are also low power indoor, very similar like FCC, so that's more or less a common part with a little bit different requirements. For example, here just 23 dBm for UEs and access points. And they have an additional mode, which is more for device-to-device communication, which is called very low power. And I have tried to draw this a little bit in these graphs that you see on the left and on the right-hand side, that you see where this is located and which kind of mode are supported: standard power, low power indoor, and very low power. If you're looking now at an actual snapshot, which countries are using this, because regulatory, you have always to have in mind, we have FCC, we have SCC, we have ETSI, but at the end of the day, every country is defining this by themselves. And this is exactly what you see also on this map here. that some countries are already adopting this use in the 6 gigahertz band with different views. For example, US, standard power and low power indoor. Canada, for example, is using all three stuff, also very low power, also with a full band. If you go for Europe, more or less what I explained, and in Asia a little bit different. And some countries, which is here in light blue, are just starting to think about using the 6 gigahertz band. But overall, and you see this also on the number of sold Wi-Fi equipment, the use of the 6 gigahertz band had some traction. And as I said, for the full power of Wi-Fi 7, also very important. I would highlight now one specific aspect, which is especially coming with this larger channel or this wiser channels. If you are using now 80 megahertz, 160 megahertz or 320 megahertz channels, the possibility that you get some interferences from others and you cannot use the channel in the full bandwidth as you would like becomes higher and higher. And therefore, a feature which was introduced already in Wi-Fi 6 is preamble puncturing becomes more and more important. You see an example, for example, an 80 megahertz channels, and if you have an other Wi-Fi network in the range, this is occupying, for example, a primary 20 megahertz channels here, which is your secondary channel, or for example, you have a DFS in this area, then you cannot use this 80 megahertz channels. You have to fall back to just the primary 20 megahertz channels, which makes it very effective because two of the channels, 20 megahertz channels, are more or less free. With puncturing, now you can also use more or less everything what is available. So that means in the same situation, you can now use 60 megahertz out of this 80 megahertz. So you see, this makes the whole thing much more effective, and it makes it more possible that you can really use these wide channels. And they have defined certain areas in Wi-Fi 6 or 802.11x. They had introduced preamble puncturing with OFDMA for multi-user operations, so that you use also the resource units that you have there. In Wi-Fi 7, 802.11be, they are doing the similar thing, extending this just for 300 megahertz. And you are quite flexible with this, with skipping certain 20 megahertz areas. And they have an additional thing, which is especially related for single user communication. So that means the whole bandwidth is used by a single user. And they can use the new feature introduced in Wi-Fi 7 for multi-resource unit, here in different scheme. This just shortly because this has also some impact on regulation. Overall, if we are just looking on the test requirements for receiver and transmitter defined by the standard, not by regulation, by the standard, then you see there's what we had also in Wi-Fi 6 and in others, typical things, spectral flatness and so on. We have, of course, a new spectrum mask for 220 megahertz, which looks also similar. Then we have new puncturing spectrum mask covering the new things, also introduced as such already before. With this multi-resource units, we have an extension now in the so-called unused tone error measurements. And I mentioned already we have new modulation scheme, and in context of this, we have also more or new EVM requirements or transmitter constellation error. Then we have a couple of test cases which are already related to trigger-based communication, and they stay essentially as they are, or as we know from Wi-Fi 6. Finally, if we look in general where the test requirements are coming from for Wi-Fi, then I just described the standard conformance, which is defined in the IEEE spec. Then there is something about Wi-Fi interoperability, which the Wi-Fi Alliance taking care, and where you get the stamp of Wi-Fi certification, which is a lot about interoperability and so on. Then there are some special areas, for example, for mobile converged devices, so mobile devices which have typically Wi-Fi, cellular and other technologies. So the CTIA is, for example, looking on this. And then there's also operators, especially fixed operators, which are also providing with a fixed access Wi-Fi access points for the home and enterprises and so on. And they use here a definition of the broadband form. But all this is essentially more, probably not nice to have, but not really required. What is really required if we would like to operate any Wi-Fi device in a certain country is regulatory compliance. And with this, I would like to hand over to Feng to give us a more detailed view on this regulatory compliance testing.
Thanks, Jörg. So, it is very clear, no regulatory compliance, no market access. Your Wi-Fi product needs CE marking for European countries and need FCC ID for US. Many other countries have similar compliance rules as EU or US has. The regulatory process for CE and FCC are totally different, and the testing behind are also different. In CE marking, Radio Equipment Directive, so RED, is the most important directive for your Wi-Fi device. Under RED, the test specifications, which are more or less defined by ETSI, are grouped in 4 categories or so-called 4 essential requirements. Today, we will more focus on the radio spectrum part. On the FCC Code of Federal Regulation 47, CFR 47, is kind of US law which defines the requirement of Wi-Fi devices, and the most relevant part is the Part 15. FCC also published many so-called knowledge data bank to use the more details of the testing. ANSI standard like C63.10, they describe the concrete test setup and the test solutions. Here, the 3 unlicensed bands are described very clear. The 2.4 GHz bands is very similar for EU and US market. In practice, many other radio devices will also share this ISM band. My colleague Jörg cleared already in this part. In the 5 GHz bands in EU, the upper part is not available as harmonized ETSI subband. Is only available in some special countries with very special limits. In the US, the whole 5 GHz bands are available. Even in 2020, FCC decision give Wi-Fi technology more spectrum shared from the DSRC technology, so which is designed for automotive. In the 6 GHz bands, the difference became more than others, because in the EU country, under the CE RED, only the lower portion is available as the unlicensed band for Wi-Fi technology. All the upper part is still not decided, but this is a topic under the ITU discussion, and the case looks like the band will not available for Wi-Fi. In US market, up to 7.125 GHz is already available as the whole UNI band for Wi-Fi devices. Here, let us check all the test cases for CE RED. We can group all the test cases into 3 groups. The first is more or less about the transmitter test cases. The test cases in all the 3 specifications, which from the ETSI, they look very similar. There are some more details are different, especially in the 5 and 6 GHz. We will come to that point later. The next group is about the coexistence test cases. Here we see more test cases are defined under the 2.4 GHz. The main reason is there are many other technologies like Bluetooth. They need also special regulation in this area. For Wi-Fi technology, the most important 2 test cases about coexistence, they are about the adaptivity and the dynamic frequency selection, which we will touch later. The third group is about receiver testing. From very beginning, the RED requires receiver test. This receiver adjacent channel selectivity is the new one, which is added to the receiver blocking. In the latest specification draft, this receiver adjacent channel selectivity is also available for both 5 and 6 GHz. So now let's have a look of the FCC test cases. In FCC test requirements, they all came from traditional EMC testing. This is the reason that the most test cases are defined as a transmitter test. The coexistence test is defined exactly only for the 5 and the 6 GHz. In the 5 GHz, we have the dynamic frequency selection is very similar to the EU requirement. And for the 6 GHz, we have 2 additional test cases about contention-based protocol. It's similar like the listen before talk, and another test case about the dual client test. So far, FCC doesn't require any receiver test. But in the recent news, which I listed here, FCC announced for a long-term improvement, they want to have a receiver test in the consideration. Means in the long-term future, we could also have receiver tests for FCC test requirement.
Thanks, Feng. Now I think we have a raw picture about Wi-Fi 6, Wi-Fi 6E, Wi-Fi 7, and also the difference between the both. But I think for our audience, it would be a kind of more exciting if we look on one or the other test case to really understand what is the difference now and what they have to care about. Could you explain a little bit more about this?
Yeah. So I would like to take some examples to clear what are the same part and also the difference between CE-RED and FCC test requirement about Wi-Fi devices. We will also try to touch which is also valid for Wi-Fi 7. We start with the first in-band emission test requirement. So here is the FCC test requirement for in-band emission. First of all, we have to be aware this requirement came to the role is only with the 6 GHz band. Means before that, they don't, in the FCC, they don't have such test requirement, especially this kind of in-band emission limit mask. The emission mask limit is defined by so-called 26 dB emission peak power spectral density. They use this to calculate the mask. In the whole UNI bands, include 5 and 6 GHz. In case channel punction, which you cleared in the last part, they don't require additional mask. They limit that scenario only with the traditional 26 dB channel bandwidth for each portion. So let's see on the CE-RED part. On the CE-RED, the test requirement looks very similar. Here, they have defined also this limit mask, but this limit mask is valid for both 5 and 6 GHz bands. So this is the first difference. The second, how to calculate this mask. This is also a little different. Here, they take this relative power spectrum density to calculate this mask. And the 1 MHz resolution bandwidth will be used. And additionally to this, they have also another hard limit, let's say is a minus 30 dBm per megahertz as additional limit line to this measurement. Very interesting is about the scenario which they have this channel puncturing, or especially for multi-channel device or multi-channel operation, very related to the Wi-Fi 6E and the Wi-Fi 7 devices. To this scenario, the ETSI standard defined several different combination of the multi-channel scenario. For each combination, they defined also this additional limit mask, have a various kind of formula to calculate especially those area, or like this more punching channel than how the limit should look like. So this limit should be calculated according to the channel combination. And hopefully, in the real practice, the most case, you will do the test with automation software, which can support you to calculate the limit in more convenient way. So this is the first difference. Let's switch to the next topic. So next topic I want to address is this dynamic frequency selection. So for years, we know the dynamic frequency selection as DFS is required for Wi-Fi devices. This method guarantees a priority of radar signal or radar applications in the 5 GHz band which the device is using. Does a Wi-Fi 7 device also need DFS? Yes, I think the answer is very clear. Because the Wi-Fi 7 devices support multi-link operation, we heard this already, which will also use the 5 GHz bands, and the DFS is very related to this area. Let's have a review about the details. First, the spectrum in 5 GHz, there are 2 UNI sub-channel. So it's the dot 2A and the dot 2C part. We need the DFS because in those areas, radar signal or radar application are available. And the EN301893, this very special case for the 5600 MHz to the 5650 MHz. So in this 50 MHz bandwidth, there is a very important weather radar working, especially for the EU country. And exactly for this, the standard requires stricter limit. We will also come to this point later. In the FCC requirement, the radar signal detection threshold is defined only from 2 values, minus 64 dBm or minus 62 dBm. One of these values will be used. But in the ETSI standard, in the EN standard, this became more difficult to get the threshold. The threshold is a linear function of the power spectrum density and also to calculate between the minus 64 dBm and the 62 dBm. So let's have a deep look which test cases or test details are required for the DFS test. We start with the CE marking or from the red aspect. This table shows you that for primary device with radar detection or secondary device with radar detection and a secondary device without radar detection, they need different test cases. The test cases itself, they are the channel availability check, radar detection threshold, in-service monitoring, channel shutdown, and also the non-occupancy time. Of course, the primary device is the master to control the whole system of this data transmission. They will need the test in this all the test cases here. The secondary device, which has a radar detection, they will not take the test cases which relate to the power up phase of the device because they follow the master or primary device anyhow. Secondary device without the radar detection, we need only the test for the channel shutdown phase, which should be cooperated with the primary device. So let's give an even deeper look of some test cases. Channel availability check. So in these test cases, it's about the device should maintain or should have a 30-second channel availability check period after the power up. In this period, the device should try to detect whether there is any radar signal available. And the transmission should not happen before this 30 seconds finished. In the next step, we have additional test cases test here. After the power up, in the next 2 seconds, a radar burst will be injected with a little higher power than the threshold, so 10 dB more. In this case, expectation is the device should go to the non-occupancy period, means don't transmission on this channel anymore, for at least 30 minutes. The similar test will also be done. Only the radar signal will be injected in the later phase of this 60 seconds. For this special case for the EU country about this weather radar, in that area, the channel availability check is not only 30 seconds, so it's up to even 10 minutes. The challenge of this test, all the antenna ports of the DUT must be connected simultaneously. Test setup must manage time synchronization and RF calibration. A couple of hundreds waveforms must be selected randomly about this radar signal to cover all several combinations of radar signals and pulse types. So we go to the next radar detection threshold. In this test, we will put the radar signal exactly to the value of the detection threshold on the DUT port directly. The test will be repeated, and the expectation is following. For the normal case, 20 repetition is required, and the whole device can detect this radar signal on this level at least 12 times. When we again to this weather radar area of the spectrum, then the 20 repetition, the expectation is also to detect the signal exactly also 20 times. So it has a more stricter requirement. The challenge of this test, as a function of DUT's transmission power spec density, the DFS detection threshold should be adapted during the test. The required number of repetition get statistically relevant results. All these make also the combination of channel bandwidth, all these combination make this test take a pretty long time. This time could be up to hours. And in practice, such tests cannot be done manually. It's consumed too many time. Most cases, we do this test with automation software. The last two test cases, in-service monitoring and the channel shutdown. So in this test item are related to the device is still in transmission, then the radar signal will be injected, and we will check whether the device will do this move to go to the non-occupation period and also do the movement to the other channel, maybe whether this correctly. So we will check, can the DUT detect this radar during the transmission? Is the channel move time less than 10 seconds? And is the channel closing transmission time also less than 1 second? That means after the detection, they can also do some short signaling to the whole system to move to the other channel, but this should also follow the limited time. The challenge of this test is similar. Accurate system acquisition for timing measurement is very important. And the post-processing of all the measurement data is required. This is also not an easy task with manual work. As we finish the CE part, red part, let's take a view about the FCC test requirement. The test items are very similar to the red requirement, and also the combination from primary client device with radar detection and also client without radar detection. The mapping is also similar. So I don't need to repeat all the details, but I want to mention one special test case. In FCC, due to they are working in this UNI bandwidth, they defined one so-called detection bandwidth test case. In this test, the target is to find the detection bandwidth. So what is the detection bandwidth? How is it defined? The test process is like following. First, they will inject a radar signal in the middle of the current band or channel, and then they will repeat this times, at least 10 times, because they need to make sure the device should detect the radar with an over 90% sensitivity. So the minimum requirement of this repetition will be 10 times, and hope you get at least 9 or 10 times successful detection. Then this will be repeated with the offset of 5 MHz to go to the direction of one side of the occupied channel of the device. And in somewhere, especially edge of this channel, you will have the case that the device cannot detect the radar signal with the certainty of 90%. Then this this frequency will be noted. The next step is to find the next edge, or like exactly spectrum upper limit with 1 MHz step. When this is finished, another side of the detection will be repeated. So remember, every channel, every injection of radar signal will be repeated 10 times at least. When we get this result, means we will find the UNI detection bandwidth for the whole device. And the expectation of this test is about the detection bandwidth should be greater or equal at least to the occupied channel bandwidth of the device. This makes sure that the device will always detect the radar independent whether the radar signal is happening in the whole area or whole channel bandwidth of the device. The challenge of the device. I said already, in order to get statistical relevant results, many repetitions of radar detection test procedure are required. Now we come to another very interesting topic, listen before talk. So listen before talk is kind of channel assessment mechanism for channel clearance assessment procedure. Simply to say, before starting the transmission, DOT should make sure the channel is not occupied by any other incumbent signals. The concrete test requirement under CE-RAD is totally different to FCC. In fact, CE-RAD needs the listen before test for all the 2.4 GHz, 5 GHz, and 6 GHz devices. The test details is more or less to answer some questions. The first is the channel occupation time, so-called COT, is less than kind of limit because this guarantees the duty cycle of the device. Those area which has a break over 25 microseconds will be considered as idle mode. The specification test standard requires the idle mode should be distributed randomly. A cumulative histogram kind of limit is defined for this random distribution. Of course, the detection threshold will be also verified for the DOT. In the RAD, 3 different kind of signal are defined. They are the additive white Gaussian noise, or FDF signal or Wi-Fi, and a 5G new radio signal is also defined. When the device detected this energy of a signal, the device is still allowed to do short control signaling procedure to maintain the data connection, maybe move to another channel. And in this procedure, this short control signaling procedure is also defined in the specification that like how many transmission is allowed, the transmission time should be short enough, and so on. Challenge of this test. The test procedure is really complex and time-consuming. High resolution of power measurement and very long test time generate huge test data in this case. Post-processing of over 60 million power measurement data will be used to get a meaningful statistical results. So you can imagine, with this test requirement, a manual testing is not possible anymore. We need definitive some test automation to support the test. When we come to the FCC requirement for the listen before talk, the things became a little easier. In FCC, this test is named contention-based protocol, so similar name as listen before talk, and the test step looks in this way. So the device is doing transmission, and incumbent signal will be injected on this transmission channel from the power minus 82 dBm. Then the power will be increased with 1 dB, and the expectation is that the device will stop transmission before this incumbent signal gets to the minus 62 dBm. And another side, when the signal is gone or doesn't exist anymore in this channel, hopefully the device will require the transmission soon back in this channel. As we are talking Wi-Fi 7 device, the spectrum play another role of this test task, because when the device is working with the bandwidth under 20 MHz, maybe 10 or under 20, then only one 10 MHz additive white Gaussian noise is required. No other signal is defined under FCC. But in case the device has a multi-channel operation, when they have the bandwidth between 20 and 40 MHz, then 2 such 10 MHz signal or white AWGN signal will be required with a different position in this channel to make sure the device can detect such a signal on the proper position. So this will be repeated twice. And then when the device is working over 40 megahertz bandwidth, in most cases for Wi-Fi 7, maybe also Wi-Fi 6E, then the AWGN signal will be repeated for 3 times, so 3 partition in the whole bandwidth. And for each test, this detection will be also repeated because here again they need a 90% certainty, means we need to repeat the test to get this statistic kind of result. Then the challenge of this test, as I said, it is a 10 repetition for each channel bandwidth is required due to this 90% certainty. And all the bandwidth mode, as I said, for Wi-Fi 7, even Wi-Fi 6E, we need to consider this. Such DUT should test all this bandwidth combination, bandwidth mode should be tested. And again, on the system level, as we are talking with 1 dB step to find this signal and so on, so precise power level threshold on the DUT antenna ports, all those need very high or good calibration of your test system. Now we come to another, hopefully the last test case which I want to clear today is about the receiver adjacent channel. So one of the receiver tests which is defined only under the TE-RAD so far, so in nowadays. The test is will have a following procedure. So first of all, we need to find a so-called P-min, so the minimum power. So what kind of minimum power? This power is about on the DUT antenna port, on the port, a wanted signal should be available, and this signal will make the DUT get exactly 10% packet error rate. To find this mean power, you need with a 1 dB step on your generator part, and then on the DUT antenna port, the exact number should be noted. So this is P min. Then the next step, this wanted signal will be increased 10 dB over the mean power which we found in the last step. This should still available on the DUT antenna port. And then in this case, of course, the DUT packet error rate will be much improved because we are a little higher or go away from the limit value. Then we will inject another interference signal, exactly the same signal. In this case, it's Wi-Fi or depends on technology. Then the power of this interference signal on the neighbor channel will be 26 dBm higher than the P-min. The expected behavior of a correct device or a good device should be the device still maintain less than 10 dB packet error rate, means the device is very robust. The same test or similar test will be repeated in the next channel on another side, then will be repeated once more with, so not the first neighbor, but one more, so this neighbor channel, and then 32 dBm will be added to the P-min, and then again expected the DUT still have less than 10% packet error rate. Then another side of the channel will be tested. So this is the procedure of the receiver adjacent channel selectivity test. How to do this test in the practice? If you go to the standard, you will see this test in such kind of block diagram, which shows which kind of instrument will be required, how the signal paths should be combined. But for me, I would like to say this is really on the theory. If you go to practice, you need to pay attention to following point. The interference signal generator and the spectrum analyzer. In this case, you need to consider we are talking Wi-Fi 7 or Wi-Fi 6E. We are working on up to 7 gigahertz, so 6 gigahertz band. And with this, of course, the instrument should also have this ability to transmit such signal. We have device always with multi-channel nowadays. We need somehow switch or combine all such antenna of device into this test setup. With this, we need such kind of switch or conditioning unit. And the best case also have some power meter inside because we need to also do the adaptation, do the attenuation, and so on. So we provide one solution in this case from our end. The most challenging thing is the following. About the companion device, signal unit or the performance monitoring device on the device side, because we are looking for this packet error rate with the limit line 10%. How to get this in convenient way? In this case, we are happy to provide you our mobile radio tester. We had already CMW500, which was the market leader for this kind of testing. I allowed today already to announce another new product. The product is already on the market for a long time, I say it correctly, but this CMX500 platform, which was designed for 5G new radio, it will stay on the topic, but this device, this mobile radio tester, we call it CoreBox, will get also the functionality to support all the Wi-Fi standard, include Wi-Fi 6E and Wi-Fi 7. With this setup, we can help to looking or to find this 10% packet error rate to make this loop of the searching process more simple, more fast, and more convenient, and also more accuracy due to all the attenuation will be handled in the instrument or handled by the OSP in this switch box. So with this, I'm already happy to tell you, to share you that our turnkey regulatory test system, TS1897, is still under the development and also get the latest upgrade. This system can support all the test cases which are required under CE RED and FCC for all the Wi-Fi standard. So from ABGN and also the latest topic which we have today, like Wi-Fi 6E, Wi-Fi 7. The system provides you all the details of the test requirement and also chasing the high precision and also granularity. Still remember, I'm talking times about how the power measurement should be done with a high resolution, sample rate, and so on. So all those details are already covered by this system from beginning. The test method nowadays with this system, most cases this is still can be done connected, but in case you have device which cannot be connected due to maybe special design of antenna that you cannot put it with the connector, you can also use kind of shading box to do the normalized testing, which is also defined nowadays in the latest specification. Last point, long-term maintenance and service. This is also our offer from the company, that we can make sure that your system are always running stable, have the best performance to help you to do the regulatory test. Such challenge which I mentioned, they are all already considered in this system. Today, we didn't mention too much about another test like radiated spill emission measurement, which is also important for the whole regulatory test. But for that, maybe we can take another opportunity to talk about the TS1896 system, which cover all the RRC test requirements. So now I give some concrete example about the regulatory test, and I hope you get kind of feeling how challenging the test could be, but also what could be our solution to support you to do the test. Now I would like to hand over to my colleague Jörg again, because Jörg has even more overview about other test solution which we are working on about Wi-Fi 7 technology, and maybe also some outlook of the technology itself.
Yes, of course. Thank you very much, Feng, for this introduction of these different test cases and also our solution for regulatory conformance test. What you also see here on this slide with our overall solutions for Wi-Fi 6, Wi-Fi 6E and Wi-Fi 7 for today and tomorrow, of course. A couple of the solutions were introduced by Feng already because they are also part of this conformance system, like our spectrum analyzers and also our signal generators, which are natively supporting Wi-Fi 7 already. You can also run this on our VSE software, which is a spectrum analyzer software using recorded data. The data you can, for example, record also with our scopes with RTP. Feng mentioned also our Wi-Fi signaling solution, which is so far the CMW500 and CMW270, supporting up to Wi-Fi 6E. Due to the further requirements for Wi-Fi that I explained in the beginning, for example, 220 MHz, 6 gigahertz band, high EVM, high data throughputs, and so on, we decided to go to the next generation of signaling platform, and this is the CMX500 OBT, where we are going to support Wi-Fi 7 as well. And not to forget, also if you would like to make non-signaling testing in a one-box fashion, then we have the CMP180, a quite new product, which is highly scalable with 2 generators, 2 analyzers on board. That is also scalable to 2 boxes with CMP Flex, so that you can, for example, test easily 4x4 MIMO and something like this. This you can do in R&D, but also in production. Of course, OTA solutions are relevant. If you still would like to have a nice box for Wi-Fi 6 testing, also the CMW100 is a good instrument for. Yeah, this just shortly to our solutions for Wi-Fi. If we look a little bit in the future of Wi-Fi or what we can expect, then let's have a look on this roadmap. So where we actually are is on Wi-Fi 7, and this is where what we described here. As I mentioned, we have actually the draft 3.0. There are a couple of other Wi-Fi standards which are probably also of interest because of quite nice application like sensing and positioning. There's a BF standard for Wi-Fi sensing. The first draft is here available. Then for positioning, the extension of positioning in the 320 megahertz band, so that, or 320 megahertz channels, so that it also fits for Wi-Fi 7. But probably most interesting is that standardization IEEE is already working on the next standard. And this has most probably the name 802.11bn. The task group will start, I think, in the November timeframe. And what is behind this? It's probably too early to explain some details, because it's, as I mentioned, in a very early stage. Applications are still extended reality, factory control, IoT, enterprise networks, and so on. And they're giving this a name that this is a new standard for Wi-Fi, mainstream standard to enhance for ultra-high reliability. What does it mean? They made a definition of reliability. They say reliability means throughput, latency, and low packet loss. And they would like to make also something for mobility or seamless transmission between base stations. So, for example, if you walk around your office. And they would also do something for reduced power consumption for access point and also for improved peer-to-peer communication. And this is just shortly what we can say today about Wi-Fi 8, or what we would like to say about today about Wi-Fi 8. Probably we will have other webinars to explain this more in details in the future. And with this, I would like to hand over again to Feng, and thank you very much.
Thanks, Jörg, for the overview and outlook. So we hope that you got more insight in regulatory test for Wi-Fi 7. You can find more information on our website. Many thanks for your attention and time.